Hey guys, how are you today? I hope you're doing well. I'm gonna run through a bunch of examples here for section 6.4, which is called Power Law of Logarithms. Yeah, and in this section, you should have reviewed the power law of logarithms as well as the change of base formula. So we're gonna run through some examples applying those now. I'm gonna do a whole bunch of them, and I've listed here what they are because they're pretty quick. So if a video gets too long, I might stop it and start again and call this one part 1 and the next one part 2. But if not, it'll just all be in this one video. All right, so question 1A on page 347, you need to evaluate log base 2 of 16 cubed. So first thing we'll do is apply our power law, which means that I can bring down this 3 to the front of the log. So now it's 3 times, sorry, 2 doesn't look very clear. Let me fix that. That's 3 times 16 base, 3 times the log of 16 base 2. All right. So next I'm going to evaluate the log of 16 base 2. And if you can't do that off the top of your head, you have two choices. Either you can change 16 to write it as a power with base 2. So that would be 2 to the 4. And then we can apply our property, our log property, that says that when the base of the log and the base of the power are the same, the answer is the exponent. So it would just be 3 times 4, which is 12. Now I said you have two choices. Your other choice would be to evaluate this log by letting it equal y or x. Let's let it equal x actually, just a little bit more convenient. X equals log 16 base 2, and then change it to exponential form. So 2 to the 4 equals, 2 to the x. Boy, I'm really off today, aren't I? I must be tired. 2 to the x equals 16, and then change them to the same base. So 2 to the x equals 2 to the 4. Solving the exponential equation, we get x equals 4. And then you would just put that x equals 4 back in for the log 16(2) here, and you would end up in the same place. Equals 3 times 4. All right. Okay, let's also have a quick look at, actually, you know what? I'm not even going to bother doing C because that's basically the same thing. Remember that if there's no base showing in the log, the base is 10, that's a common logarithm. So let's just go straight to 1D, which is evaluate the log of 0.1 to the 1/2. So same idea, I can apply my power law, bring that 1/2 down in front, multiply it by the log of 0.1, and of course the base is 10, common logarithm. So again, we have the same two choices. We can write log of 0.1 with base 10, which would be 10 to the negative 1, because 1 over 10 is 0.1. And then that would make it equal to 1/2 times negative 1, applying my log property that says that when the base of the log and the base, I don't even know what that is. The base of the log and the base of the exponent are the same, then the answer is the exponent on the power. So that would be equal to negative 1/2. Or if you prefer, you can solve it as I did above here, solve the log portion first and then multiply it by 1/2. Either way is totally fine. Just make sure if you use this method that your form is clear. So maybe do this, solve the log off to the side, and then come back and put it into this step. Next question, 2C. Evaluate the log of cubed root of 81 all to the 6 base 3. So really what we need to do is try and get this whole mess here into base 3. So first thing I can do is write 81 as base 3. So I have cubed root of 3 to the 4, because 81 is 3 to the 4. Still have a 6 on the outside there. Then I need to remember that a cubed root is the same as an exponent of 1/3. So I'll apply that here, changing my cubed root to a base of 1/3, and then it's still to the exponent 6. And now I have power of a power of a power. So I just remember my exponent rule, power of a power of a power. I just multiply all the exponents together. So 4 times 1/3 times 6 actually comes out to 8. If you need to, do it on your calculator. 4 times 1/3, sorry, 4 times 1/3 times 6, yeah, is 8. Okay, and then that means that that log is equal to 8. Okay, next question was 3D. 3D, solve for t to 2 decimal places, and the question is 500 is equal to 100 times 1.6 to the t. So this is a similar question to what you had in the investigation number 1. And so we'll want to get this t out of the exponent so that we can solve for it, right? First thing we need to do though is get rid of this 100 because it's in our way. We really can't do much with it yet. So I'm going to divide both sides by it. So I get 5 equals 1.06 to the t. And then you should have discovered by now that if you take the log of both sides of this equation, then it will allow you to apply power law on this side and bring that exponent t down in front so that it comes out of the exponent and it's multiplied by log 1.06. Let me just go back a step. The reason why I can take the log of both sides is because I can do that with any function. As long as I do exactly the same thing to both sides of an equation, then I can apply any function to both sides of an equation, right? Even when I'm multiplying by a number on both sides or adding by a number on both sides, it's really a function. It's the function of multiplication by a number or the function of adding a number. So all I'm doing here is taking the logarithm of both sides, and as long as I do it to both sides because it's an equation, then it's legal. So I have log 5 equals t times log 1.06. Going on to the next page, I just rewrite that. Log 5 equals t times log of 1.06. And to isolate t, I just need to divide both sides by log of 1.06. Right? If you needed an exact answer, you would leave it like that. Since it says to 2 decimal places, you just put that into your calculator. Just make sure that you do log 5 and then either close the bracket. On my calculator, the bracket doesn't get closed automatically after the 5, and then divide by log 1.06, sorry. Right, so I get 27.6 approximately. 2 decimal places, 27.62. What I was saying about the bracket is that my calculator, when I do log 5, it opens a bracket, but it doesn't close it automatically, which means that if I just went straight to dividing by log 1.06, then it would divide only the 5 by log 1.06, not the entire log 5. And I know a lot of calculators do that. So just be aware that you need to close that bracket on the 5 first and then divide by the log 1.06. Or alternatively, you could put in log 5 and press equals or enter, get an answer, and then divide it by log 1.06. So if you're getting an error, if you're not getting the right answer, then that could be the source of the problem. Next question, 5a. 5a says evaluate corrected 3 decimal places log 23 base 3. Now since this is not log 10, this is not base 10, you can't do it on your calculator directly, but luckily we can apply the change of base formula and we can make both bases 10, and then we will be able to do it on our calculator. Now just note here that making both bases 10 is the most convenient way to solve it with the calculator, but they don't have to both be 10. For example, they might both be 2. That would also be fine, and the change of base formula applies in that case as well. The only problem is you can't use your calculator to do it, so it's not really that useful. Unless these numbers could then be written as base 2, but they can't. So we're not going to do that. We're going to just keep them as base 10 and use the calculator. So log 23 divided by log 3, and I get to 3 decimal places, I get 2.854. All right, what have we got left here? The last question I wanted to do was 6D. And it's pretty quick, so I think I'll just do it even though this video is getting a little long. 6D. We need to write as a single logarithm the log of x plus 1, log of x plus 1 over the log of x minus 1. And so this is backwards of the change of base formula, right? So with the change of base formula, let's just write it down over here. The log of b base a would be equal to the log of b over the log of a, both with the same base, and 10 is usually a convenient base to use. So let's see, how can we do this backwards? Well, in this case, the x plus 1 would be b, and the x minus 1 would be a. So this, written as a single logarithm, would be log of x plus 1 base x minus 1.